Okay, now we have done the RH stability criteria methods to determine the stability of the systems, and then we found that there are three ways to fill up the table. The first one is normal case, special case 1, and special case 2, right? Okay, now what we're going to do is we want to see what is the use of RH criterion in the design of control systems, right? Okay, now let's look at these systems, open loop systems, where we have the input is R of S, the output is Y of S, right? And the K is the gain controller. This is our systems. We find the open loop transfer function. We found that this K over S squared plus 3S plus 2. Okay, now we see that the denominator of the systems is fixed, right? So it is, if the system is stable, then it is stable regardless of any K values. That means the K can range from 0 to infinity, alright? So, but the system's properties remain the same. You see that? Okay, now based on this, RH criterion doesn't help us much. It's only provide us the stability for the probably one off, right? Once we calculate this, then we know the system is stable, not stable. That's it, right? But now let's move on to the closed loop systems. Now we have a closed loop system like this, and then we found that this transfer function is like this. After we calculate this, we got this K over S squared plus 3S plus 2K, 2 plus 1K. I think we learned this in the previous topics, right? In the closed loop and open loop systems. Okay, in this case, you see that the denominator of the systems has K in it, right? The K element in it, meaning that changing K values here not only change the numerator of the systems, but also change the denominator of the systems, or we call it characteristic equation of the systems. Hence, the stability of the system would change according to K values, right? Okay, now this is our characteristic equations or denominator of the systems. We need to verify what is the K values here to keep the system stable, right? We know that for certain value of K, the system will be unstable, right? So right now, we use the same way we fill up the RH table, right? So like this, we have 1, 3, 2 plus K, 0 here, right? So same thing. And then we found that the next, this the S column will be 2 plus K, because that 3 multiplied by 2 plus K minus 1, that's 0 over 3. We got this, right? So now this column would be stable if there's no sign change. That means as long as K values will keep this row positive, the system is stable, right? So let's see this. S squared plus 1 is 0, right? So we have 1, 3, 2 plus K. Here, it's 0. This one here, right? Let's say we put A1. So A1 is equal to 3, 2 plus K minus 1 plus multiplied by 0 over 3, right? So simply, there's a 0, 3. So this is A1 here, okay? A1 here is a 2 plus K. So we know that from RH criterions, to keep the system stable, there must be no sign change here, right? So we can use this 2 plus K greater than 0, right? So K must be greater than, so this is minus 2, right? k is greater than minus 2. Right. So as long as the value of k is greater than minus 2, that means when we say greater than minus 2, minus 1 is greater than minus 2, right? So it will keep the signs, this a1 signs positive, right? So as long as k is greater than minus 2, the system is stable. But if k is minus 3, right, which is smaller than, so this is the condition of k. So for the system to be stable, k must be greater than minus 2, right? So let's say let's plug any values that outside this range. K2 minus 3. Let's say k is 3. Then this a1 here, okay, that's a1 equal to minus 1. So that will be minus 1 here. So the system will change the sign. So there will be sign change on the first column. Positive, 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 negative. That means there will be one roots on the right hand plane. The system is unstable. So to keep the system stable, we need to make sure that k is always greater than 2. So in this case, for the systems to be stable, no sign change on the first column of RH array. For this to happen, 2 plus k is greater than 0, hence k is greater than minus 2. So the range of k for the system to be stable is k is greater than minus 2. Okay, right? So hope you understand this. So why we use this one? We can, if we have a complex system, we can use this one to determine whether this system is, what is the range of k, right? That is number one. Okay. Okay. Number two, we have this system, right? This another systems. When we fill up this, we have something like this. All right. So we have two conditions here that determines what is the range of k. The first condition is k minus 4. The second condition is 2k plus 13. That means the k has to be in certain range, right? So for the systems to be stable, k minus 4 is greater than 0 and 2k plus 13 here must be greater than 0. That means this term here and this term here must be positive. So in this case, k is greater than 4, right? Then k greater than minus 0.5. In this case, um, for the first column to be all positive, k has to be greater than 4, right? Because this one is at the same time fulfill this criteria. So we just take one criteria to make sure that the system is stable. Otherwise, if we take 3, although it's you know, fulfill this criteria, but it doesn't fulfill this, just take this as the range of k. Okay, apart from that, we also can determine the value of k so that the system is, when the system is marginally stable, because as a k increases, the system poles roots will actually move from positive to negative. That's why the system calls the system unstable, right? If okay, this is our explained imaginary, right? So based on this, right, we know that certain value of k will actually makes these the root will shift to the next, to the on the left hand plane, right? Let's say we have, this is a second order systems, right? So maybe I would say at certain value of k we have 1, 2 poles here. As we increase, it will probably increase further, and then when k is greater than 4, k is less than 4 or maybe less than this, the system is unstable because the range to be stable k is greater than 4. Maybe less than k less than 4, the system is not stable, right? So maybe somewhere the system on this side. Okay, what we need to find is when is the system cross that point here, right? Because we know that the system is unstable here, but we don't know exactly what is the point. We don't know what is the point, but we can be sure that if the system cross that, it will actually fulfill the special case 2, right? In the special case 2, remember special case 2. So there is when there is or roots on the imaginary axis, right? So that means if for special case 2, this row must be 0, right? So to make this row must be 0, that will fulfill special case 2, and then we know that at that particular k, the poles, the roots of the systems are on the imaginary axis, right? So because if k equal to 0, k equal to 4, now if k equal to 4 in this case, 4 minus 4 is 0, right? Okay. And then the whole thing becomes 0. Okay. If k equal to 4, so we need to, we can simply say that when k equal to 4, the system is on, the roots on the imaginary axis, right? So we can find the rest of the system roots, but as long as this root is 0, we know that the system is on the imaginary axis, right? So now we know that the range of k to be stable, k must be greater than 4. If k to be equal to 4, then the system is marginally stable, right? Okay, that becomes a very useful method to determine what is the range of k for the system to stable, and then what is the value of k when the system enters at marginally stable, right? So because if we increase k values here, the roots of this will change. Let's say at k equal to 1, k to 1, if you find the you factor this root, there will be different sets of roots for different k values. But how do we know that? So what is the k value that give us two imaginary roots? So using this one, we can determine exactly what is the k value when the roots of this denominator on the imaginary axis, right? So I think that is the applications of the RH criterions. Other than that, we can determine the stability of any systems. We could also determine the range of k, and then what is the critical or the k value so that the system is at marginally stable system, right? So I hope you understand this, and then our test will be covered up to this topic, right? Thank you very much.